This is a short experiment to see how low the frequency will go when I double the capacitance and double the inductance of the circuit. Here I am using my 12 volt setup just because it's easier to change the work coil since I don't water cool it, and I'm not fan cooling the board either. These two conditions limit the runtime of the system. The good news is, though, that this setup gets me down to the 38 to 40 kilohertz resonant frequency range. That's close enough to my earlier 30 kilohertz goal for me to move on to see if this lower frequency penetrates steel any more effectively than does a frequency in the range of 87 to 113 kilohertz, which is what I get with the stock system using various diameter coils that came with them. Visit my earlier videos for the details on the sizes of these other coils. My next move after this video test will be to move my double C double L test up to my 48 volt force cooled system. Here's the setup for today's test. I know it's a mess, but there it is. Again, this is my 12 volt system. With the basic 1000 watt ZVS driver and the stock coil and the stock 6 times 0.33 microfarad capacitors for a total of 1.98 microfarads, and a 2-inch ID coil, I get about 87 kilohertz resonant frequency. With the same 2-inch ID coil, when I doubled the capacitance, I went from 87 kilohertz down to about 62 kilohertz. On this setup, when I went from the stock 2-inch ID 6-turn coil to the present 12-turn coil of the same diameter as the previous one, still only using the stock capacitors, I got down to about 62 kilohertz. That's about the same change I got by just doubling the capacitors. Now, for this demonstration, I will use the 12-turn coil and double the capacitance. We will also look at the waveform at one gate as a reminder that having only 12 volts for a supply is not good for keeping the MOSFETs cool, since the device spends most of its on time in the linear region. And we'll be using the little scope here to read the frequency. Really, we'll see the gate waveform, but we're using it primarily to read frequency, and then we will use the Tektronix scope up here just to take a look at the signal across the oscillator at some point. I'm just kind of going to be focusing in really close on the various components for today. This is the double capacitors. This is the 12-turn 2-inch ID work coil connected to the board. These are the heavier leads than I used when I just doubled the capacitance, and also soldered terminals to try to have as little bit of a voltage drop across those connections as possible. Here's my analog current meter, which I always suggest you have. This one only goes 10 amps because I don't draw more than 10 amps on this test. And then I just recently added one of these little 12 volt meters just to read my battery, so I could see what happens as I start loading things down, and so I know enough to stop the test before I get down to the point where I might have a voltage so low that I won't that one MOSFET will stick on. And then of course this is the on-off switch to turn the power on and off to that system. Okay, 12.7 volts, no load, no current. Switch on, about 0.8 of an amp. Voltage drops to 12.5. Sorry about the sync, but that's the gate wave. Can you see that it's 43 kilohertz? I'm going to stick the 1/2 inch bar in there. Current is at 1 amp. I stick the bar in, goes up to 8 amps. Frequency drops to 38.56 or something like that. Here you see a really nice sine wave while I have the circuit on and idling. And I'm going to put a 1/2 inch bar in there, and we see the current goes up to about 8.6 amperes, and it's still generally a sine wave, but you see it's got a bunch of little rough edges on it. I don't know what they're from, but anyway, that's what the scope looks like, and you can see the frequency slowing down as I go. The horizontal time base is set at 5 microseconds per division. The thing's been on for maybe 30 seconds. Voltage has dropped to 12.3 already. Again, the idling frequency is 43.5 kilohertz. With nothing in it, if I put my 1/2 inch pipe test piece in, voltage goes up to about 8 amps again, and the frequency 40, 43, 41, something like that, bouncing around, but anyway in that vicinity. I'm going to try pushing the hold button here. Where, okay, there, hold. Not too sure what I'm seeing there. 43 something, anyway. Okay, 40.4. Again, you can see my thicker wire behaving well. The coil is warm, 100 degrees. MOSFETs are cold. Capacitors are cold. Chokes are barely above ambient temperature by a degree or two. My capacitor wires here to my double capacitance is barely above ambient temperature. I'll put my 1/2 inch square pipe in here, go up to 8 amps for 10-15 seconds. 11.8 volts, sorry about the telephone. And this is 38.5 kilohertz I'm reading there. Better than the 1/2 inch pipe. My wires barely got warm at all, so that's been an improvement. Okay, well, I think I'm about at the end of the test. Again, just looking at the gate signal, it's not square. Looking at the output across the work coil, a nice sine wave. Again, with about 1 amp flowing at idle. My battery is down at 12.3, so it's a good battery and it is recovering. In closing, so the board still seems to work okay at these lower frequencies, and this is good news. Now that I have this information, I will make these changes to my force cooled unit, which is here. And that, of course, is my 48 volt setup. The goal is to see if the same amount of power supply current at this lower frequency will more efficiently transfer energy to a ferrous load. And as I think I already mentioned, although we're only on 12 volts, the components stayed pretty nice and cool during this test. Thanks for watching.